Yeah, so this is one of the very important result. It's called rank nullity theorem. It says that T from Rn to Rm is a linear operator. Okay, and then uh, n, which is the dimension of Rn, and this equals to dimension of the range of T plus dimension of the null space of T. Alright, so this is the result that we are going to prove. Yeah. So the idea is let dimension of RT is P with P less or equal to M, and since RT is a vector space, therefore it has a basis. So what is the basis that it has? We can define that. So let u1, or rather v1, v2 up to vp belongs to w is a basis for RT, right? Of course, since this is in RT, therefore there exists u1, u2 up to up, all vectors in v. I mean, yeah. So w I can call here as Rm, and these are the vector in Rn. Okay, because in general this is taken as w and this is taken as v. This is the idea. This was v and this was w generally, but it's okay. So these are the vectors in this one, such that, what is such that here, T of ui is vi with I from 1 to p. Now we claim that these vectors u1, u2, up are li. Number one, this is claim that u1, u2, up are li. So this is obvious. What you do is sigma alpha I ui is 0. This means T of sigma alpha I ui is 0, and this means sigma alpha I vi is 0 because T of ui is vi. But this vi is, since vi's are li, since vi are li, why? Because it's a basis. So basis is the linear independent set. So therefore this implies that alpha I is to 0 for all I equal to 1 to up to p. Okay, this is fine. Now by basis extension theorem, by extension of basis, we can get n minus m, or rather n minus p vectors, what are they? Maybe w1, w2 up to w n minus p, where in Rn, such that, and of course these are all Li vectors, because when we extend the basis, so there are many procedures. For example, Gram-Smith orthonormalization process, or there are many ways we can add Li vectors to a set, and that eventually can be made to the basis of entire space. So these are the Li vectors, and therefore this u1, u2 up to up, and w1, w2, wn minus p, all these vectors, these are n vectors, and they are in Rn and forms a basis in Rn and forms a basis of Rn. Okay, so we done. Now what remains to prove to the theorem? It's sufficient to show that this sufficient to show that, to prove the theorem, it is sufficient to show that a dimension of nt is n minus p. So clearly ui does not belong to n of t, because this one t of ui, because t as t of ui is vi, which is in range of t and non-zero. Okay, so this is not there. So clearly the only possibility that wi can be in null space of T. So our claim is that wi belongs to null space of T for all I equal to 1 to up to n minus p. Okay, so if we show this, then we are done, because we have n minus p vector, all are belonging to nt. So therefore this is the basis, and we cannot get anything more than that. So suppose not to start by the contradiction. Suppose not. That means wi does not belongs to nt for some I, so I can call it that k does not belong to nt for some k. Okay, so this means that t of wk is non-zero. But then where it would be? This would be in the range, and therefore this vector has to be spanned by the basis of the range space. Therefore t of wk equal to sigma beta I and vi, and I is from 1 to p, which is equivalent to saying that sigma I is from 1 to p, beta I T of ui, and then by transferring whole thing we get T of wk minus beta I ui summation I is from 1 to p. This is 0. What does this mean? This means that this whole vector is actually in null space. So we can, from here, we can say that so wk minus this is 0. This means that wk minus sigma beta I ui I is from 1 to p belongs to null space of T. Then clearly who can spawn this? The vectors other than wk, and all ui will possibly spawn this at the most. Therefore I can write this: there exists some gamma I in R constants with the I from 1 to up to n minus p, but I not equal to k. So wk minus sigma beta I ui equal to sigma gamma I and and then I is running from 1 to n minus p with I not equal to k, because k is already here. Now transfer everything this side, we will get that wk minus sigma beta I is from 1 to p minus sigma gamma I wi is from 1 to n minus p and I not equal to k. This whole thing is 0. Now remember, these vectors form a basis by virtue of this property, that they are all in Rn and form the basis of Rn. Therefore this is a linear combination of all these vectors. Therefore all the coefficient has to be 0. This means gamma I has to be 0, beta I has to be 0 for all I from 1 to up to p, and for all I from 1 to n minus p and I not equal to k. And this is 1 here, 1 into wk, and therefore 1 also has to be 0. But this is a contradiction. 1 cannot be 0. This is the contradiction. That means our original assumption that we have assumed that wi is not in nt is wrong. Therefore wi has to be in nt. So we have that all wi belongs to nt for all I equal to 1 to up to n minus p, and they are all Li vectors and they are the maximum Li set, and therefore they have to be the basis. So hence dimension of nt is n minus p. So we have proved it. The dimension of nt is n minus p. We started with taking the dimension of rt is p. So p plus n minus p is n. Therefore the theorem is satisfied now. This can also be started by assuming, we have started by assuming that dimension of rt is p, but one can also start by taking that dimension of nt is p and then show in the equivalent way that dimension of rt is actually n minus p. That is also possible. Okay, I think you might have enjoyed this video. If you have any concern, comments, kindly respond to us. Thank you.